Hey, so I want to talk with you a little bit about geologic maps. This is a project that, we started back in class and we had tracing paper out. We talked about stratigraphic principles. This was a long time ago. Um, so that was the cross-cutting relationships and the superposition, the oldest thing being on the bottom and the youngest thing being on the top. And it turns out that all of that is actually really useful. And I asked you to make your own geologic map, but I want to back up here for a second and talk a little bit about geologic maps in general. And hopefully, this will make it a little bit easier for you to complete that tracing paper map that you started and that I think just about everybody was able to take with them. So, what we're looking at right now is a geologic map of the planet of Mars. And this was authored by several people at the US Geological Survey. And it's pretty interesting to think about doing a geologic map of a planet that nobody has walked on yet, but it's not uncommon. What people do is they try and distinguish one rock type from another. And you started doing that. We've been doing that in class when we look at Google Mars and then figure out some age relationships. And that's what you were starting to work on when we were looking at the tracing paper. The problem with geologic maps, especially when you sort of look at them like this one is meant to be printed out poster size and looked at on a huge scale, is there's just tons of information and it's really overwhelming and hard to know where to start. So don't get overwhelmed. There is lots of information on each map, and these are going to be resources that you can really use later on in the semester to help research particular locations. And you're definitely going to have some assignments about that. Lots of people have worked on detailed geologic maps for parts of Mars. So what you'll notice is that there are a lot of colors, and each color defines what we think of as a geologic unit. And that is something that is large enough in scale to show up on a map. It doesn't all have to necessarily be the same exact rock or type of deposit, but it needs to be related and maybe have a similar appearance or a similar chemistry, probably a similar age. So those show up on the maps, and I'm going to talk about those more in a second. And then the other thing that the maps often show is age relationships. So what's older, what's younger, and I'll show you how those are indicated on the map. Because what's really cool is that once you understand how this geologic map works, you can look at geologic maps from anywhere and they contain the same type of information. And you can learn how to decode that and use it. So I zoomed in I zoomed in on part of that large scale geologic map. And you can see over here in the bottom left corner, there's Olympus Mons, that's in one color. There are craters that are in this like lime kind of color. There's some blue over here and purples, and um, there are all these different colors, but some of the colors are used more than once. So this lime color you can see is usually associated with craters and crater ejecta. Um, oops. The purple color over here, it also repeats in here. That's something distinctive. The big volcanoes are both similarly colored, Alba Mons and Olympus Mons, so that sort of implies that they're probably related. The other thing you'll notice is that inside most of these, and I'm going to point to one with a cursor right now, there are capital letters and then lowercase letters. And these codes are actually really useful because they're telling you something about what they think the age of that feature is. So if we zoom in even more, this is actually an area we've looked at a little bit in class. these teardrop shaped islands. I had you sketch some of those when we were looking at Google Mars to look for river features. And you can see this is all mapped in sort of this blue color. Um, and it's got this H, capital H, and then lowercase to. When you're looking at a geologic map, the capital letter is always telling you something about the geologic age. So you notice in here we've got a capital N, a capital H, and somewhere, yeah, here it is. We've got a capital A. And if you recall, I know this is, we're pushing it out here, but the Martian timescale has three major divisions: the Noachian period, the Hesperian period, and the Amazonian period. So right away, what this map is telling you, just from these codes that are on here, is that this brown material, this is Noachian or presumed Noachian. This blue material, the HTO, and we're going to look at this in a little bit more detail in a second, but this HTO is Hesperian, and these lime green crater-related deposits are Amazonian. And I've put them up here in late Amazonian, but actually we don't know. I could draw the arrow from anywhere in here. What you do know, though, is that you can see that they're youngest because they're cutting across some of the older deposits. So both by superposition, they're sitting on top, and because of cross-cutting relationships, these have to be younger, and that's one of the reasons they were assigned an Amazonian age. So the colors and the codes are really useful. If we go back to the big map for just a second, so now you've got all of these different colors, but you can kind of start to make sense out of that. Over on the right-hand side, we've got this really complicated legend. And this is actually organized. These are always done this way. This is actually organized in a really useful way. So there are different categories, there are different types of deposits, but within each category, the stuff that's at the bottom of the list is oldest, and the stuff that's at the top of the list is youngest. So that would be true in this category. There's another category here. This stuff is oldest, and this is youngest. And then if you look over in this part of the map, what they're doing over here is each of these columns is one of the categories, and they're showing you which color is youngest and which color is oldest. But what that's trying to get you to do is to realize which rocks from different categories are maybe the same age. So there might be some river deposits that are the same age as a volcanic rock somewhere else. So that's called a correlation chart. We'll look at that. If we just think about this HTO unit again, you can actually zoom in on the legend and it will have all of this information in there for you. So we've got HTO, and it tells us the full name of that unit. So it's the Hesperian Transition Outflow Unit. And it's telling you that it's in places where there are these branching channel systems. It's near the Mars Pathfinder site. It tells you, it says it superposes units, so maybe on top of those, and it's overlain by another one. But this is about where it's located. And then over here, this is actually really cool because it tells you what their interpretation of those rocks are. Now remember, nobody's actually walked around there, so we don't know. But their interpretation is that it's an outflow channel, fluvial meaning river related, from catastrophic erosion of highland rocks. And it's got islands of underlying bedrock exposed. And we saw those islands when you were looking at this area in Google Mars. So this is pretty cool. And now when we go into this correlation chart, it's in these transition units. So this is transition from the highland area on the southern hemisphere to the lowlands on the northern hemisphere. Um, so we've got this being the same age as maybe some of these polar units or some of these volcanic units. So for your assignment, I'm actually going to break this into a separate video, and we'll come back to this in a minute.